All right, we're going to be doing weak acids today, and then we'll do weak bases on Thursday. So on this problem, we're going to be solving the steps that are on the bottom of the previous page. First, we need to write the major species in the solution. So we have hydrofluoric acid, obviously, and we're going to write the dissociation equation for each of them. So it breaks up into hydrogen ions and fluorine ions. And our Ka is given 7.2 times 10 to the negative fourth. But HF isn't the only thing that is contributing hydrogen ions. Water is also contributing hydrogen as well as hydroxide ions, because all of these are going to be aqueous solutions. So the Ka for that, or the Kw really, is 1 times 10 to the negative 14th. We need to decide which acid is going to be the strongest, which is going to contribute to our hydrogen ions. And HF is stronger based on the Ka values. So the water equation, we're not going to need that one anymore. So we'll erase that one in a second. Next, it says to write the equilibrium expression for the dominant reaction. So hydrogen ion times fluorine ion. Fix that. Over HF. So same thing that we had done before. We're going to need to set up our ice table. So I'm going to erase the water equation just so I can save some room. So while I'm doing this, you can go ahead and set up your ice table. So initially, I only have HF, it says, and I have 1 molar of it. So 1 for that, 0 of everything else. Our change is minus x, because it's all 1 coefficients. So 1 minus x, and x. I'm going to plug these values into my equilibrium expression. And so we have our hydrogen and fluorine are both x, so I'm just going to simplify that to x squared. And then 1 minus x. Like your notes say, go ahead and solve for x the easy way, which, remember, that's going to be taking away your minus and plus x's. So now we basically have 7.2 times 10 to the negative fourth is equal to x squared. So I'm going to solve for x. The 5% rule, we'll see what that is in a second. That has to do with percent dissociation. But in this case, our x is equal to our hydrogen concentration, which is also equal to our fluorine, but we only care about our hydrogen currently. So that's 0.027. So now we can find our pH by plugging it into pH equals negative log of H. And we get a pH of 1.57. Okay, go ahead and try this one on your own, or at least set up what you've got and then resume play. Alright, so I'm going to write my dissociation equations for each of the reactions. So I have hypochlorous acid, which is 3.5 times 10 to the negative 8. And I also have water, but that one's 1 times 10 to the negative 14th. So this one is going to be the stronger acid, so I'm just going to write this equation. But make sure you check, because water sometimes can be the stronger acid. Write my equilibrium expression. And so I know the steps are tedious, but walk through all the steps because it'll save you from messing up. And on the AP test, you'll usually get points for these steps that may feel monotonous, but just do them anyway. So our initial concentration is 0.1, 0 of everything else, minus x, plus x, plus x. So 0.1 minus x, x, x. Plugging it into our Ka expression. Again, we can ignore minus x. Solving for x, we're going to get our concentration of H, which is 5.92 times 10 to the negative 5th. So now we can plug it into our pH equation. pH equals the negative log of 5.92 times 10 to the negative 5th. Its our pH is 4.23. And notice our x was very, very small, so that's why we can ignore them. Alright, in this case, we are given two acids, HCN and HNO2. Both are weak. And so we need to compare those two as well as water to see which one is going to be contributing to our hydrogen ion concentration the most. So I'm going to write my dissociation equations for each of them. So all three are contributing hydrogen, but only one is going to contribute it enough to affect the pH. The others are going to be so small that it's not going to matter very much. So looking at our Ka values, we can see that HNO2 is much stronger than the other two acids, although it's still a weak acid. So it's going to be our main contributor to hydrogen ions. So first we're going to find the pH, and to do that we're going to use only the HNO2. So I'm going to erase the other two for now. So go ahead and set up your equilibrium expression and your ice table and see if you can find your pH. Okay, now this problem is exactly the same as what we've done before. The only difference was we had to decide out of the three which was the strongest. And remember, the larger the Ka, the stronger the acid. So we start with 5, 0, 0. We got our minus x, plus x, plus x. So 5 minus x, x, and x. And so our Ka is equal to H ion times NO2 ion over HNO2. Plug everything in. Again, we can ignore our minus x because our Ka is still less than 1, which all weak acids are going to be less than 1. We can solve for our x, which is our hydrogen ion, just like every other problem we've done. So our x is equal to 0.045. And pH is equal to 1.35. Alright, to find our cyanide ion, we're going to need to look at the only thing contributing to our cyanide, which is HCN. So I'm going to clear this page. So I have more room to work. I will need my hydrogen ion concentration though, because it's still in the beaker, although it didn't come from HCN. So all three substances are in the beaker: HCN, HNO2, and water. So I need to write my dissociation equation for HCN because, again, that's the only thing contributing to my cyanide. The difference, though, I'm only going to write my Ka. Alright, so we're starting with 1 molar HCN. So let me move this over to set up my ice table. Notice everything looks pretty much the same. The difference, though, is I'm not going to have 0 hydrogen, because, again, I do have hydrogen already in the beaker from the HNO2, and it's enough where I cannot ignore it. So I'm starting with 0.045 of the hydrogen. But I don't have any cyanide because HCN hasn't broken up. Everything else is the same, minus x plus x plus x. And so this is a way that they can use the other acid. They'll ask you what's the concentration of, like in this case, cyanide, or the anion of whatever acid wasn't the strongest. So you'll need to remember to use the hydrogen ion from the strong acid in the initial concentration. But other than that, it's the exact same type of problem. So plug in our equilibrium concentrations into the ice table. We have x times 0.045 plus x and that's actually the cyanide times the hydrogen ion, over 1 minus x. Remember that we can ignore the minus x's and the plus x's, so I'm able to mark out both of those. So I need to divide by 0.045, and that's going to be my hydrogen ion. Or sorry, take that back, my cyanide. So x is equal to cyanide. Notice x is only equal to cyanide. If I was trying to find my HCN concentration, I'd have to plug it back in. And so cyanide is equal to 1.38 times 10 to the negative 8 molarity. So make sure you can solve this type of problem. Alright, go ahead and pause the iPod and try this one on your own. Restart when you think you have it. Alright, because it's an acid, but they don't tell us what acid it is, I'm going to use HA. HA is the general formula for an acid. So if you don't know the acid, or you don't know the formula of the acid because it's a strange one, you can just use HA. HA breaks up into hydrogen ion and A ion. So we can write our equilibrium expression using those values, our constants. Set up our ice table just like before. So 0.4400 minus x plus x plus x. So 7.5 times 10 to the negative fifth is equal to x squared over 0.44 minus x. So x is equal to my hydrogen ion. Can ignore the minus x. So in case you're having problems solving it out, we do times 0.44. So x squared is 3.3 times 10 to the negative fifth, then square root, that gives us x, which is concentration of H, which is equal to 0.0057. So the negative log of that is 2.24. So looking back, our correct answer should be A. Alright, percent dissociation, also known as percent ionization, is the amount the amount dissociated, and our percent dissociated is going to be X basically, over the initial concentration. So whatever was originally given times 100. And the more dilute a weak acid, the larger the percent dissociation. So the more we dilute it, the greater the percent of dissociation. So on here it says calculate the percent dissociation, which is basically saying what's the X of acetic acid. They give us the Ka and they give us the solution. So I'm going to write my equilibrium expression. You probably want to write the equation first. I got a little ahead of myself here. Great, so here's our equation that goes along with that equilibrium expression. So acetic acid breaks up into hydrogen ion and acetate ion. Set up my ice table just like before. So we start with 1 molar solution, 0 and 0, so minus x plus x plus x. So notice this problem solving out the exact same way, the only difference is going to be the end. Our Ka was given. So Ka times x squared over 1 minus x. Solve for x. And you get 0.0042. And instead of finding the pH, which we've done previously, they just want to know percent dissociation. So we need to find our x, which we found, and put that over our initial concentration, which was 1 times 100. And that'll tell us the percent that broke up, which in this case is 0.42%. Okay, go ahead and pause the iPod and try solving this one on your own. Alright, so we have our equation, which is the same as what we had before. We can write our Ka expression, which is the same as before. And like I said, most of this is the exact same as part A, but if this was a test or quiz, you'd want to make sure that you're showing all of your work. So we have 0.100 minus x plus x plus x. Plug it into our expression. Solve for x, 0.0013. And remember, x over initial concentration, which in this case is 0.1 times 100, gives us a percent dissociation of 1.3. And I don't know how I got the 4. So 1.3%. Notice this is a more dilute solution. It's 0.1 instead of 1, and our percent dissociation, which was much greater than the previous problem in A. Alright, on this one, they gave us the percent dissociation, which is going to change the problem slightly. And we're going to look for the Ka value. So notice the difference. They gave us the percent. We're looking for Ka, so we don't know what the Ka is. So you should know your percent dissociation equation. Percent is equal to x over initial, which in this case is 0.1, times 100. Plugging in what we know. We know 3.7 was the percent. We're looking for x. We know initial times 100. So solving that out, dividing by 100, multiplying by 0.1, we get x, which is 0.0037. So I'm going to write out our expression. So lactic acid, when it breaks up, it's going to give off hydrogen and lactate. Set up our ice table, so 0.100 minus x plus x plus x. So it'd have 0.1 minus x, x, and x. But we do know what x is because we knew the percent dissociation. So when you know percent dissociation, you can figure out x, which means we can plug that into our equilibrium concentrations, and we get 0.0963, 0.0037, and 0.0037. Since we know all of our equilibrium concentrations, it's just like last unit, we can plug it straight into our Ka expression to solve for Ka. So Ka is equal to 0.0037 squared over 0.0963. So our Ka is 1.42 times 10 to the negative fourth. So somewhere between 1.42 and 1.43. Okay, going to try this problem on your own. When it says 0.3% ionized, that's the same as 0.3% dissociated. Alright, so again, I do not know what acid this is, so HX goes to H ion plus X ion. So that should be X ion up on the top. So we have 0.5 minus X, X, and X. Again, they gave us the percent ionized, so we can solve for X. When we solve for X, that's our hydrogen ion concentration. So we'll be able to solve for pH. Okay, so similar to the last problem, but we're just solving for pH instead of Ka. But at the end, we could have easily solved for Ka as well if it would have asked. So plugging it in, 0.3 equals X over 0.5. X is 0.0015, which is our concentration of H. So pH is equal to 2.82. So looking back at our answer choices, D is the closest answer. Alright, last problem. Going to try solving this one on your own and then restarting the iPod. Alright, so write our dissociation equation. HA goes to H plus and A minus. 0.5500 minus X plus X plus X. So 0.55 minus X, X, and X. Write our Ka expression. Plug our equilibrium values into our Ka expression. Ignore the minus X. We can solve for X, which is 0.0908. And now that we know X, we can find percent ionization. So it's just like before, put X over initial, which was 0.55. And then times 100. And we get 16.51%. Which, if we had to choose from the answer choices before, we would get A. And I'll explain Thursday why it wasn't exactly 16, but it basically comes down to we probably shouldn't have ignored the minus X, but since it's multiple choice, we can get that answer.